24, he had been made a professor at the University of Rome, and thanks to his commanding presence, his researchers had nicknamed him the Pope. Unlike the Pope, though, he was broke. Italy's dominance in science had long fallen off since the days of Galileo. If they needed a piece of equipment, they built it from homemade scraps. If they needed protection from radiation, they would sprint back and forth down the hall to avoid getting a lethal dose of whatever chemical concoction they had just made. You see, they were trying to do the unthinkable. They were trying to create a new element. The periodic table back in Fermi's time looked a little like this. Similar to what you're familiar with, but with a lot of pieces missing. You'll notice a few gaps in the middle regions, specifically elements like technetium, francium, astatine, and promethium. But the biggest missing piece is at the bottom. We're missing like a full row and a half. What you see here right now are all the chemical elements that humans had found in nature. Just sitting around in the atmosphere as gases, in the ground in rocks, even a couple liquids. Many of them are stable. A good number of them are safe, so long as you don't eat, inhale, or drink them. A decent portion, however, are not, and are in fact quite dangerous. Radioactive samples that are firing off millions of invisible electrons that can penetrate into your bloodstream. Radium, discovered by Marie Curie, almost certainly killed her. Her daughter, Irene, very likely died from exposure to polonium, the other element discovered by her mother. So maybe you understand now why Fermi didn't mind having to sprint up and down his lab if it meant extending his lifespan by a few years. So how does one go about creating a new element? Well, on paper, it's simple. You add or remove protons. Hydrogen has 1 proton, helium 2, lithium 3. And if you keep doing this, count all the way up the periodic table, you'd eventually get to the heaviest element in the known world up to that point, element 92. You know it as uranium. Here's the other part of the picture. An element is determined entirely by its proton number, but the number of neutrons can vary. That neutron number makes certain elements more stable than others. Carbon-12, with 6 protons and 6 neutrons, is extremely stable. It will stay in that form untouched for billions of years. Carbon-14, with 6 protons and 8 neutrons, is radioactive. It's got an energy imbalance that it wants to rectify, and at random it will convert one of its extra neutrons into a proton, and fire off a dangerous electron to account for that energy imbalance. We call this beta minus decay, and what you're left with is an element with 1 extra proton. That's 7, aka nitrogen. Look at that! Purely by having 1 too many neutrons, the carbon destabilized and transformed into an entirely different element. Fermi's idea was to go to the furthest edge of the periodic table, uranium, element 92, and fire neutrons at it to try and artificially induce beta decay. If it worked, you'd be upgrading element 92 into 93, and if you could do it twice in a row, possibly even 94. Here's a fun problem though. How do you even know if you've created a new element? After all, you don't know what it looks like or what its chemical properties are. In this case, Fermi and his team had to rule things out by verifying which elements they hadn't created. They compared the result with the chemistry of all known elements down to lead, element 82, and couldn't find a single match. Unstable elements often lead to something called an alpha decay chain. That's when a nucleus spits out 2 protons and 2 neutrons. It leads to a leapfrog effect, where element 94 turns into element 92, then 90, 88, and so on, until they reach a stable element, which is often lead. The other possibility was that they had succeeded. They had made elements 93 and 94 for the very first time. The discovery catapulted Fermi into overnight fame. He was Italy's pride and joy, and obviously, he got first dibs on naming those 2 elements. Although he was under a lot of pressure to name the element after a symbol of ancient Rome, fascisium, from the word fasces. Recently, however, the symbol had taken on an entirely new and terrifying meaning. It was the symbol of fascism, and the man pushing for the name was none other than Benito Mussolini. Yeah, Fermi did not follow this suggestion. 4 years go by. It is November 10th, 1938. 2 things happen that day. In Germany, it's the Night of Broken Glass. In Italy, a wave of anti-Semitic laws are introduced. Fermi's wife Laura was Jewish, and her passport was on the edge of being revoked. So when the phone call came in that day at 6 p.m. that Enrico Fermi had won the Nobel Prize in Physics, their family didn't think twice. Fermi, his wife, and his children packed their bags and immediately traveled to Sweden. They did not return to Italy, and instead settled in the United States. And almost immediately after they arrived there, Fermi got the news. He had been wrong. He hadn't created elements 93 and 94. He had done something much crazier. He had made an atom explode. When Fermi declared that he had made new elements, He did so because the chemical properties didn't match up with anything as light as lead. Turns out, he should have looked even lighter. A group in Berlin had repeated his experiment, and they saw something really unexpected. They were seeing krypton and barium, two elements that were far too light to be the result of an alpha decay chain. But if you add up their proton numbers, 36 and 56, you get 92, uranium. Fermi had split an atom in two, a process that releases an absurd amount of energy. In reality, Fermi had discovered nuclear fission, a discovery that would go on to fundamentally reshape the upcoming war that he had just fled from, a discovery that would go on to dictate a global power struggle that would last for half a century. Entirely by accident, Fermi had falsely claimed the discovery of two new elements, and half a century later, one man would make a similar false claim, but entirely on purpose. This is a story about Viktor Ninov and the race for the periodic table. I gotta show you something. This is the periodic table. I'm betting you recognize it, but it doesn't show the whole picture. Each element has a unique number of protons, but each element can have any number of neutrons. We call these nuclides. Some are more stable than others. There are dozens of elements, but there are thousands of nuclides. Here's what you're looking at. The x-axis is the number of neutrons. The y-axis is the number of protons. Each square is a possible nucleus. This is hydrogen, exactly 1 proton. This is helium, 2 protons, 2 neutrons. Every possible proton-neutron combination that has ever been observed is present on this chart. Every time we go up a row, that's a new element. I don't think my audience has a lot of overlap with football fans, but if it does for some weird reason, think of this as scoregami, but for chemistry. A checklist where we mark things off that didn't exist before and maybe never will again. See, inside a nucleus is a pair of competing forces. On the one hand, you have the strong nuclear force. At extremely short ranges, it is able to glue together protons and neutrons into bundles. But on the other hand, you have the repulsive electromagnetic force. Protons all have a positive charge, and thus want to push each other apart. Only when the strong nuclear force can overcome the electromagnetic force can you have a stable nuclei. The neutrons, which are electrically neutral, serve as a kind of packing material. Because they don't repel each other, they can act as a buffer for the protons, making a nuclei more stable. Notably, the same element can have different numbers of neutrons, with some being very stable and some decaying immediately. We can actually see those stable nuclei quite clearly. They are the tall pillars in brown. The height on this chart represents the half-life of a given nuclei. A single half-life is the time it takes for a sample to be reduced by 50%. The taller it is, the more stable it is. One thing you can see is that for the lightest elements, the most stable combinations are those where the proton number equals the neutron number. See this line? Perfectly balanced. You can trace this line from hydrogen up until about calcium, and then the trend starts to diverge. For most elements, it's actually more stable to have more neutrons than you have protons. If we follow the path all the way up, we end up at lead. This is the path of stability. As soon as you stray even a little bit from that path, you plunge into the realm of radioactivity. The red pillars here are essentially stable, with half-lives in the billions of years, but by the time you make it to the oranges, you have a half-life in the minutes. A couple hours go by and a sample could be reduced to nothing. And if you touch the water, in blue, those half-lives are in the seconds. And the deep blue, well, that's milliseconds. Or in the worst cases, the half-life is so short we can't even measure it. For some of these nuclei, there's a good chance there's only ever been one of them in existence in the entire universe. A nuclei so unstable it could never occur on its own, but we forced it to. The beauty of this chart to me is that it's almost like a topological map of our journey through the periodic table. Like a mountainous peninsula surrounded by a raging sea of radioactivity. The sea even has tides. Way up here in this chasm, you'll often get swept away in an alpha decay chain. That's when an element spits out 2 protons and 2 neutrons. It moves 2 spaces diagonally downwards, like this. A cascade that doesn't stop until you reach a stable element. On the south side of the mountain pass, there's a different type of tide. Fermi's beta minus decay. You lose a neutron, but gain a proton, like this. If you're smart, you can use this to go up a step, potentially creating a new element. But on the other hand, to the northern side of the mountain pass, there's beta plus decay. You lose a proton, but gain a neutron. No matter where you are, however, every part of this sea is fighting you. The tides of radiation always lead you back to the same place. No matter where you started, eventually you get pushed back to shore, to the main path of stable nuclei. Some people refuse to accept this. They push back, trying to explore more of the sea and potentially uncover more and more land. Enrico Fermi was one of the first. Fermi began his journey here, and he made it as far as the uranium chasm. Over the course of the next 50 years, several different labs would make the same pilgrimage up this mountain, and every new pilgrimage would fill out more and more of this chart. The protagonist of our story, the intrepid Viktor Ninov, claimed he had made it up to here. It's pretty far, huh? To meet him, we've got a bit of a journey ahead of us, and we're gonna need some help. To cross this sea, we're going to need a captain. Fermi would go on to do important things. His most well-known achievement is building the first nuclear reactor under the stands of a Chicago football field. But he stopped pursuing the hunt for new elements. That chase would be taken up by an entirely different team. The discovery of the real element 93 was weirdly unceremonial. On the west coast of America at the University of California, Berkeley, American physics was in full go big or go home mode. Berkeley at the time was home to the world's biggest cyclotron, the best tool in the biz for element hunting. A cyclotron is a type of particle accelerator. It uses magnets to rapidly spin charged particles around in circles and then smashes them into targets. Now, this isn't one of the multi-mile rings that you're probably thinking of. Those are actually too powerful for making new elements. For this, you need something a bit more delicate. Berkeley's state-of-the-art tool was 60 inches in diameter, and it could pelt a uranium target with neutrons, again hoping for Fermi's predicted beta decay. And one day, after finding a radioactive lump that matched no known samples, element 93 had officially been confirmed. We now know it as Neptunium. The credit for this discovery went to Edwin McMillan and Phil Abelson, but the celebration was short-lived. Their publication was met with silence from the academic community. No one dared acknowledge the breakthrough, lest it give the Germans any inspiration. Although America hadn't yet joined World War II, they were preparing to, and so McMillan and the rest of the lab's top scientists were soon drafted into the war effort, working on radar, or in some cases, the Manhattan Project. That left a vacant seat to take over the element hunt. That's where our captain comes in, Glenn Seaborg. As the descendant of Swedish immigrants, they had left their home country with the last name Sjöberg. Upon reaching Ellis Island, an immigration official decided that their new name would actually be Seaborg, and it stayed that way. This customs officer had no idea that his half-assed spelling attempt would one day make it on to the periodic table. Glenn, from a young age, went wherever the tides of life took him. After his family decided to move from icy Michigan to sunny California, an 11-year-old Glenn decided to add an extra N to his name because it looked cool. Can't argue with that, Glenn. And on another day, as a 24-year-old chemistry student strolling through the Berkeley campus, someone from the radiation lab stopped him and asked if he could help them separate out some chemical samples. He was just the first chemist they found on campus. Seaborg would eventually work his way up through the lab, and with Edwin McMillan gone, he asked if he could take over as the new captain of the element hunt. Although McMillan never got to try it out, he had come up with a recipe for element 94, and good old Glenn was going to get the first crack at it. If you add one neutron to uranium, it beta decays into element 93. But say you fired a proton and a neutron. The proton would immediately bump it up into element 93, and then the extra neutron would have a chance at beta decaying, upping it one more time to element 94. It really is like an absurdly delicate game of Jenga. So yeah, that's how you make plutonium. It's safe to say that the discovery of plutonium was kind of a big deal. It's actually an even better fuel for a bomb than uranium, which was the original plan for the Manhattan Project. And thus Seaborg and his team were immediately drafted to Chicago to work with, oh, hey, it's our old pal Fermi. There they spent months artificially making enough plutonium to flatten a city or two. It was difficult and hazardous work, and at one point a lead brick fell and broke a beaker, and 25% of the world's entire plutonium supply was soaked into a copy of the Chicago Times. But the Manhattan Project is a story that's been told many times by people better equipped to tell it than me. The story we care about involves Glenn Seaborg and Berkeley. By this point, they have enough plutonium for their bomb, so Glenn and his team are free to ponder some other questions. Why stop at 94? Surely the periodic table didn't end at such a weird number. And they didn't even have to reinvent the wheel. Instead of starting with uranium, just start with plutonium and fire neutrons at that. To go back to the Jenga analogy, you're trying to build a taller tower, but the bottom rows are radioactive, and they keep disappearing on you. But as long as you're building the tower faster than it's disappearing, maybe you can find a new element. Now at this point, we're going to pick up the pace a bit. There are still a lot of missing pieces between us and our friend Viktor Ninov. If you want to read more, I highly recommend the book Super Heavy by Kit Chapman. Essentially though, the timeline went something like this. Element 93, discovered by Berkeley. Element 94, Berkeley. Element 96, discovered by Berkeley members in Chicago. Element 95, Berkeley members in Chicago. 2 atomic bombs are then dropped on Hiroshima and Nagasaki, killing upwards of 250,000 in the immediate blast and poisoning the ground and air for decades after. Next up was element 97, once again found by Berkeley, and since they definitely earned it at this point, they named it berkelium. Element 98, hey, guess what? It's Berkeley again. They named it californium this time. With 4 elements in a row, the New York Times joked that they should have just gone with universitium, ovium, californium, berkelium. It was at this point that the Nobel Academy finally acknowledged Berkeley's achievements, and so Edwin McMillan and Glenn Seaborg shared the Nobel Prize in chemistry. Next up was elements 99 and 100, and this is going to sound extremely stupid. I swear I'm not making this up. America dropped a nuclear bomb in the middle of the Pacific Ocean, sent fighter jets through the very, very top of the mushroom cloud to collect samples, raced like hell to get the rapidly decaying lumps back to Los Alamos in New Mexico, where they were then analyzed to see if they had made any new elements. Yes, and unbelievably, they did. Since Berkeley helped out with the analysis, they were co-credited with the discoveries of 99 and 100. These were named after 2 of the field's greatest minds, Einstein and Fermi. Both of them had passed away just months earlier. And soon enough, there was element 101, again found at Berkeley, named to honor the creator of the modern periodic table. It truly was one of the most dominant streaks in scientific history. Every other lab was left playing catch-up and could do nothing but watch as Berkeley added nearly half a row to the periodic table. And there was nowhere else to go except further and further up. As of 1945, the 4 earlier gaps in the table had been filled. Elements 43, 87, 85, and 61 had all been isolated. If there were more elements out there, it was only going to get harder and harder to find them. From this point on, they would come to be known as the Super Heavies. As for Glenn Seaborg, he was once again going where the tides of life took him. His career took a turn when he received an out-of-the-blue phone call from John F. Kennedy of all people. He was about to be named the next head of the Atomic Energy Commission. Later, he would become a close confidant of Lyndon B. Johnson, and they were apparently such good friends that Seaborg was regularly invited to the White House to just come hang out and chat. After he had made the fuel for the first atomic bomb, Seaborg would push hard for treaties that would limit the spread of nukes. This is not an attempt to absolve him of his role in that, but I think it's important to fully contextualize it. This is where Seaborg diverges from our story, but Berkeley does not. Every element in the streak from 93 to 101 had been discovered by a team with some sort of tie to Berkeley. From this point on, it would not be so clear-cut, and the controversy would play out on a geopolitical scale. There are a lot of famous Einstein quotes out there, but there is one I saw for the very first time while researching this video. This is what Einstein had to say on the topic of making new elements. It would be like shooting birds at night, in a country with not that many birds. So true, bestie. And he's not wrong. Element hunting is essentially like gambling. The basic setup is easy enough to describe. You have a target and you have a bullet. Except both the target and the bullet are so small they're invisible, and also the target is almost certainly radioactive. And even if you do make a direct hit, there's a good chance you'll break apart or even destroy parts of your target. So this is less like aiming a gun at a target and more like a game of roulette with the absolute worst odds imaginable. If you take just one spin, the odds of hitting the exact right pocket are not good. But if you take 5 million spins at the roulette wheel, your odds go from basically impossible to just barely within the realm of possibility. Yeah, the odds are terrible, but sooner or later, you're bound to get a hit. For element hunters, this means aiming a beam at a target and leaving it firing for literal months, which you can imagine gets very, very expensive. Depending on the lab and the type of beam, firing continuously for just one day can cost somewhere in the tens of thousands of dollars. A few months of beam time then is easily in the millions of dollars. We have a lot of uranium on Earth, about 5.5 million metric tons, and even the shortest half-life is still 25,000 years. So getting a large enough uranium target to fire neutrons at isn't really a problem. So making plutonium is easy enough. But then for the next level, your target needs to be plutonium. And then after that, it's curium, Einsteinium, etc. Each time, your target's half-life is getting shorter and shorter. 1 gram of uranium costs about 13 cents. A gram of Einsteinium costs about $27 million. Most casino goers can't afford that kind of buy-in. But in theory, if you've got unlimited time and unlimited money, element hunting gets a hell of a lot easier. Berkeley, situated in the richest state in the richest country in the world, had the most money and the best equipment, so no wonder they had the leg up. But that's the beauty of the casino. It was just a matter of time until another lab got lucky. While the Americans were busy building a bomb, the Soviets were lagging behind, embarrassingly so. Admittedly, they were very occupied holding off the Germans on the Eastern Front and had focused all of their scientists on metallurgy. The Soviet nuclear program owes its start to one random volunteer lieutenant on the Eastern Front, Georgy Flerov. Prior to the war, he had been following the topic of nuclear fission quite closely, only for all publications to abruptly stop talking about it in 1939, of all years. He found this bizarre, as the ability to harness the power of an atom was like the most exciting thing to come out of physics in decades. He soon connected the dots. Oh my god, they're all making bombs. Flerov, against all conventional wisdom, wrote directly to Stalin and basically demanded that the Soviets devote as many resources as they could to nuclear technology. Flerov was, surprisingly, not punished for this insubordination, but instead made a key player in the Soviet nuclear program. Following the war, however, Flerov changed his focus. He wanted to hunt elements. He founded JINR in Dubna, a small Russian town. Soon, it would be America versus the USSR in the hunt for elements. Wow, science being used as a tool by rival superpowers to help fight a Cold War? Never heard that one before. Couldn't be me. It's safe to say that nearly every new element from this point on would be hotly contested, and any and all evidence would be denied by either side. These were the Transfermium Wars, and here's how they went down. First, a small lab in Sweden claims they found element 102. No you didn't, says Berkeley. Your equipment is cheap and bad and your tests not thorough enough. I agree, says Dubna, and then they both bullied Sweden until basically nobody believed Sweden had actually found anything. Berkeley tried some experiments of their own, which accidentally caused a radioactive dust spill that resulted in their lab being evacuated, and 27 people had nearly 3 months shaved off their average lifespan. Dubna then swoops in with even better results and claims 102 for their own. Then, Dubna claimed 104, 103, and then 105, so fast that all the Americans could do was try and nitpick their data and make those same elements, but just better. It didn't help that each side had their own preferred types of evidence. To confirm a new element, the Soviets preferred using spontaneous fission. Their detectors were cheaper, and nuclei that split in half were big enough that they were guaranteed to detect something. The Americans called this unreliable, as you had no idea what was being split in half. They prefer to track alpha decay chains, the long line of elements feeding into one another. Because of this split in methodology, the data from this period is a mess to make sense of. Some of it was good, but dismissed by the other side because of bias. Some of it is straight up wrong, but was pushed out the door due to urgency. It's almost as if this sort of cutthroat competitive structure leads to sloppy work. I sure hope that doesn't come back to bite anyone. For now, the element hunt had stalled. By the time you get up to element 102, your half-life is less than an hour. Before, you could rely on other dedicated labs to manufacture you enough of an element. They could ship it to you, and then you could start firing your beams at it. With a half-life of less than an hour, you couldn't even get a sample across town, much less an intercontinental flight. The quantities they were working with were getting smaller and smaller. When Berkeley claimed the discovery for curium, element 98, they did so after generating around 5,000 atoms of it. By the time they got to element 101, they had only created 17 atoms to claim the discovery. Soon enough, it was likely that any new elements would only be created one atom at a time. Singular atoms that would decay before another could join it. This clearly wasn't the end of the periodic table, but the element hunt was becoming too expensive and too impractical to continue. At least, not without a breakthrough. Out of the 218 total winners, only 4 women have ever won the Nobel Prize in Physics. The first was Marie Curie all the way back in the ceremony's 3rd year, for her studies of radiation. She would be the only woman to hold this title for nearly 60 years. It wouldn't be until 1963 that Maria Goeppert-Mayer would break that trend. Like many of the pioneers of nuclear physics, Maria was an alumni of the Manhattan Project. After the war, she began studying elements and their half-lives, and what at first glance appeared to be random, soon she began to see patterns. Certain nuclei were reliably more stable than others. It was almost as if there was magic numbers of protons and neutrons. Maria visualized protons and neutrons as a set of dancers engaging in a waltz. The dancers are circling around the room and spinning around on their feet. You can fit more dancers in the room if you pair them up, and by having adjacent pairs spinning in opposite directions. Certain magic numbers of dancers fit more cleanly than others. In technical terms, this results in nuclei with a higher binding energy, which in turn gives a more stable nucleus. To date, the known magic numbers are 2, 8, 20, 28, 50, and 82. In element terms, that's helium, oxygen, calcium, nickel, tin, and lead. The critical way markers on the mountainous path of stability. Notice that these magic numbers are all even. This demonstrates that protons and neutrons like to pair up to become more stable, like dancers pairing up for a waltz. Additionally, elements with a magic number of either protons or neutrons tend to be extremely abundant. And finally, at the end of a naturally occurring alpha decay chain, you will always find a stable element with a magic number. For an extra special example of this, take lead, the heaviest stable element. It's considered double magic, with both a magic proton number and a magic neutron number. There's a reason it is the very last step in the mountain path before you get to the Great Chasm. And the magic numbers theory had one last crazy prediction that gave the element hunters some hope. There was a magic island out in the middle of that sea. This island should be situated at 114 protons and 184 neutrons, right here. Make no mistake, this is not an island you could settle down on. You're still up to your neck in water, but your toes can just barely brush against the sand at the bottom. For just a moment, you can catch your breath before the tides of the sea will eventually come in and sweep you away again. And if this was true, maybe you didn't need to work your way up from the bottom, element by element. Maybe you could do it in reverse. Start at the edge of the cliff and launch yourself all the way to the island. From there, whatever element you made would likely decay into an alpha chain, and you generate all of the other elements on your way back down. They needed a catapult. Element 106 marked a turning point in the element hunt. The last 4 elements were contested by both major sides, but element 106 was found and announced by Berkeley and Dubna the exact same month. For once, both teams agreed that it was too close to call. The tactics at this point had changed. Element 93 was made by slamming a neutron into uranium, the biggest possible target and the smallest possible bullet. By the 1980s, the thinking had changed. Why use an expensive radioactive target when you could use a much cheaper and much stabler target like lead? And instead of firing something small like helium, fire something medium-sized, like chromium or iron. Think about it. Lead has 82 protons. Iron has 26. 82 plus 26 is 108. Counterintuitively, this is actually more reliable than trying to get a single proton to join a massive nucleus. Nuclei closer in size balance each other out, and the resulting product doesn't eject nearly as many neutrons during the fusion process. Now, if this sounds too good to be true, yes, there is a reason no one had tried this before. A source as heavy as iron would need an entirely new beam technology designed from the ground up, and a detector that was more sensitive than anything that had been invented yet. The Soviets were out of money and had no hope of going any further, and the Americans over in California had, for the first time, run out of ideas. The stage was set for Player 3. This is GSI. Situated in Darmstadt in Western Germany, GSI had more than enough money to bankroll the new expensive equipment that the Soviet team couldn't afford, thanks to the post-war West German economic miracle. Their new beam could fire elements as heavy as chromium, iron, or even bismuth, all of which would hit a lead target. Over the course of just 5 years, this led to the discovery of 107, 109, and 108, in that order. For the first time, it was a true 3-way race in the element hunt. Berkeley, Dubna, and GSI. As the 1980s came to a close, there were 9 elements that needed official names. In comes IUPAC. Now, I once got into an argument with a commenter who claimed that IUPAC isn't actually the body that decides the names for the chemical elements. It's the scientists who come up with the names, but only in the same way that 6-year-old me totally got to choose my own bedtime and my mom had no say in the matter. IUPAC laid out the basic rule for what can be considered an element discovery. Namely, that an element must be stable enough to exist for more than 10 to the negative 14 seconds. It's the time necessary for electrons to form a cloud around a nucleus. But IUPAC also had to choose who got to name which element. Otherwise, we'd have separate American and Soviet names for at least a dozen elements. And even in the rare cases where they could agree on a name, they couldn't agree on which element should get that name. At least 3 separate elements have, at some point, been referred to as Rutherfordium. IUPAC would foolishly spend years trying to find a compromise that satisfied everyone, but eventually settled on a compromise that made everyone just slightly unhappy. Among these new names, for the very first time, was that of a living scientist. Element 106 was called Seaborgium. The captain had left a permanent mark on the sea that he had traveled for most of his life. He passed away 2 years after the name was made official at the age of 86. It was a fitting end because Seaborgium would be the last element discovered at Berkeley. The collapse of the Soviet Union hit the Dubna lab hard. The Russian economy was a garbage fire, and even its prestigious element hunting team wasn't immune to the fallout. For a while, it seemed doomed to close down. If you weren't Russian, you left the lab for your home country. If you were Russian, you left the lab for a private sector job where you'd actually have a salary. In the end, what saved it was renting out the accelerators to private companies and a partnership with the unlikeliest of allies. Livermore Labs in California also had an element hunting team, and the Russian team kept their lab alive by joining forces. For the world, this was a good thing, but for Berkeley, this was yet another hurdle. Their fiercest rival had just teamed up with a fellow Californian lab. It would be outright petty to dispute any element claims that came out of such a partnership. Dubna Livermore first set their sights on element 110, the next in the sequence, but their attention soon shifted. They were about to attempt something that had only been dreamed of before this point. They were finally making that catapult. Their recipe was calcium-48 fired at plutonium-244. They're going to skip 3 whole rows and aim for element 114. And in 1998, it worked. 114 protons, but only 176 neutrons. Remember, the theoretical center of this island of stability was supposed to be over here, to the east, with 184 neutrons. But the half-life of this atom of 114 was in the realm of seconds. Not milliseconds, full seconds. The island of stability was real, and they had found the beginning of its shoreline. IUPAC wasn't entirely convinced. They wanted some more data, so the Russians kept at it. They'd work on trying to reproduce 114 more reliably, maybe even aim for 116 as well. The German team at GSI had other ideas. Although the country had suffered its own depression due to reunification, they got back on their feet much faster than Russia, and they had spent the last 5 years upgrading their equipment. But the lab at this point was being shared by several teams with competing projects. The main accelerator had a busy queue, and you'd often only get a few weeks with the accelerator before another team got priority. The element hunting team had already spent a few of their precious weeks calibrating the beam intensity, and now they only had 4 weeks left before the next team would bump them off the schedule. It was an extremely short window for this sort of experiment. The team decided to swap out the beam to fire nickel at lead. After just 1 day, they saw the first sign of element 110. They were unbelievably lucky. Their luck continued when they found out the next experiment was delayed by 17 days. So they kept at it. They swapped out the lead target for bismuth. Bam! 1 extra proton gave them element 111. 2 elements in just as many months. A year goes by and they try firing zinc at lead. At first they get a weird reading, but they keep going. In a little over a week, they find 112. The German team had once again done the unthinkable. A hat trick of 3 elements in a row. Move over, Berkeley, the crown has officially been lost. Berkeley at this point was nearly 20 years out from their last element discovery. The Russians were probing the island of stability, and the Germans were doing victory laps. They needed a secret weapon. And so, they orchestrated a coup. Enter, finally, Viktor Ninov. Physics doesn't often lend itself especially well to the idea of a rising star in the same way that music or film does. It's a glacially paced field of study that happens behind closed doors, and where it's hard to find a photo of someone that hasn't been JPEG'd into oblivion. But if physics did have a rising star, Viktor Ninov certainly fit the bill. Ninov was born in Bulgaria in 1959. As a young man, his family emigrated to West Germany. Ninov would go on to study physics at the Technical University of Darmstadt. Eccentric does not do Ninov justice. He regularly signed his emails with "You're crazy Bulgarian." He loved biking, and even played the violin. After he met his future wife, Carolyn Cox, she turned him into an avid hiker. He would often venture into the mountains with colleagues, and had even survived an avalanche accident that left him badly injured. His travels were not limited to the ground, however. He once sailed the Pacific Ocean on a 45-foot sailboat, and somehow he still had time to be a pilot, flying a single-engine, 4-seat Aero Commander. However, none of that holds a candle to my absolute favorite of his antics. He and a colleague were on a quest to visit every Italian restaurant in Darmstadt, where they would always order the spaghetti carbonara, and they would rank them all. Let me be absolutely clear. This is a grade A bit. I would also do this. This is so funny to me. A Bulgarian man ordering an Italian pasta dish from every restaurant in a German city. 0 notes on this. Besides being well liked by the entire team, he was also essential. In 1988, GSI upgraded their old computers, and Ninov took the lead on this. He was the go-to computer tech and even wrote a custom software package called Goosey. It was a one-of-a-kind, state-of-the-art software for analyzing decay chains of radioactive samples. Whereas before you had to manually look for analog detection spikes, element hunting had gone digital. He had found himself a niche in a field that is already filled with niche experts. And over the last 10 years, he was able to add a pretty sweet bullet point to his resume: co-discoverer of elements 110, 111, and 112. So given all of this, it was an outright scandal when Berkeley headhunted him from GSI in 1996. The man who orchestrated this headhunt was a man well into his 80s. Al Ghiorso's story is a wild one. One day during the mid-1940s, he was installing an intercom system to the Berkeley lab and ended up meeting 2 secretaries. One of the women, Wilma Belt, would later become his wife. The other woman would later become the wife of Glenn Seaborg. Through this mutual friendship, Glenn recruited Al when he joined the Manhattan Project because Gyorso was gifted at making homemade Geiger counters. After the war, when they returned home to Berkeley, Gyorso was Seaborg's right-hand man, and they had been together for every element up until 101, when Seaborg left for his political appointment. That left Al Gyorso as the de facto head of Berkeley's element hunting team. He was meant for this job. Let me paint you a picture. In the 1940s, Al Gyorso supposedly held the world record for the longest range ham radio. He had extended his personal one so far, he could pick up stations in Ohio all the way out in California. He never collected the prize though because he was illegally operating without a radio license. Back when Berkeley had their accelerator on one end of the campus and the chemistry lab a mile up a hill, Gyorso would jump into his Volkswagen Beetle and in the middle of the night race at illegal speeds up the Berkeley Hill so that they could get their sample tested before it decayed into nothing. Once he nearly ran over a security guard who pulled a gun on him and he just kept driving. When Berkeley had their accidental radiation emergency when hunting element 102, it was Al who exited the building last after he calmly shut down the accelerator. Nearly half a century later, Al Gyorso was the last remaining key figure from Berkeley's glory days. His second world record, a little more prestigious than his radio one, was for the most elements discovered. So when Al Gyorso calls Viktor Ninov a young version of himself, you hire that man. Gyorso was so excited that this brought him out of semi-retirement. Berkeley had a new rising star and an opportunity to be on top once again. With Ninov put in charge of the data analysis side, they needed someone to be in charge of the equipment end. That man was Ken Gregorich. He had overseen the construction of Berkeley's newest piece of tech, the Berkeley gas-filled separator. Now, they just needed a recipe. Dubna and Livermore had just made the claim for element 114. IUPAC wanted more data. Already months behind, Berkeley would have to act fast to try and scoop the element with a more convincing experiment, but they would have to use a different recipe than Dubna. Dubna had used plutonium-244 and calcium-48, neither of which Berkeley had enough of to run experiments. Also, the other problem is that the amount of required plutonium is actually illegal to use in a place as densely populated as the San Francisco Bay Area, so there was that whole thing. But they had yet another recent addition to the team who had another wild idea. Robert Smolenchuk was on a visiting scholarship from Poland. He was a theoretical physicist who had previously run some calculations that were mildly controversial. One colleague called his calculations simply mind-boggling. Robert was saying, skip everything from 113 to 117, aim for 118. His plan was simple: fire Krypton 86 at a lead 208 target, both of which are easy to acquire and, better yet, not radioactive. Now, conventional wisdom said that this recipe was too good to be true. Yeah, the protons add up to 118, but the probability of the reaction was thought to be near impossible. Not Robert, though. He had published a paper in which he showed calculations where this recipe was actually more likely to occur than others. Going back to the roulette analogy, element hunting is all about probability. You gotta consider what the odds of getting a hit are against the cost to keep the beam running for weeks. And to quantify this probability, physicists had come up with a delightfully silly unit of measurement. A barn is a unit that is somewhat of a hybrid between cross-sectional area and the probability of a collision between two particles. It quite literally comes from the phrase, couldn't hit the broadside of a barn. Given its origin, one whole barn is considered a comically large target, as in it would be very difficult to miss a target of one barn. When it came to element hunting, the size of this target had been shrinking exponentially for decades. These days, reactions are measured in picobarns, trillionths of a barn. Take a look at this chart. On the horizontal axis, you see the atomic number of the element you're trying to create, and on the left-hand side is the estimated measure in barns. You'll notice that this is a logarithmic scale. As you go from element 102 to 110, the probability has gotten worse by a factor of nearly 10 million. Talk about diminishing returns. One thing you might notice, however, is the probabilities go up very slightly around element 114. This is one of the indications that the magic island of stability isn't just a mirage, and suggested that the Russian team were onto something. Now, element 118, though, that's a terrible barn measurement. Most recipes were predicting not even a single picobarn. When you get down to the picobarn level, if you have your beam running constantly, you might be able to produce one single atom a week, which you might not even detect. And you're out hundreds of thousands of dollars. Once you go below a picobarn, you'd be lucky to get even a single atom for an entire month's worth of beam time. And that's why Robert's recipe was so controversial. His paper argued that his recipe could give you 670 picobarns. If he was right, it would be a game changer. Not everyone was convinced, but the nice thing was that this recipe was low risk with a potentially high reward, and they needed a calibration test for the new machine anyway, so why not use Robert's magical recipe? No one was expecting an immediate breakthrough, and yet that's essentially what they got. The experiment began on April 8th of 1999. Most of the lab had left for Easter break. The one exception was Ninov, who stayed behind to analyze the results. 11 days later, the lab director, Darlene Hoffman, would get a phone call. Her first instinct was that it would be bad news. It had only been 11 days. Ken Gregorich assured her that it was quite the opposite. Darlene had every reason to assume the worst. Chemistry in the 40s was not a job intended for women. Darlene Hoffman had to wade through years of systemic discrimination to help change that. When her father passed away suddenly, she asked a professor if she could miss tomorrow's quantum chemistry test to plan the funeral. The professor made her do the test on the spot instead. This was, to use the industry term, horse shit. She wrote it with tears in her eyes. She still got a B. She persevered and finally got hired as a nuclear chemist at Los Alamos. But when she got there, she was told that women weren't hired to work in that division. While HR sat on their ass pretending to do anything, Darlene found her soon-to-be supervisor at a party who immediately fixed the situation. And then her security clearance magically went missing. Wow, that's weird. It took 3 more months before Darlene got access to the lab, and she had just narrowly missed out on what could have been a career highlight. Remember that atomic bomb that the fighter jets flew through? They went to Los Alamos, and because of bureaucratic nonsense, she missed out on being part of the team who discovered elements 99 and 100. A loss that filled her with rage that she funneled into her work. And now, as she entered her 70s, she was beloved by nearly every chemist that she came into contact with. And she was in charge of Berkeley's element hunting team. So yes, she wanted an element. She wanted it a lot. Just a few minutes after the phone call, Gregorich, a visiting professor named Walter Loveland, and Viktor Ninov had come to her office. Ninov had found something incredible in the early results. Notably, Ninov didn't want to show Darlene the results at first, but he was outvoted because why wouldn't you? To better illustrate what he had observed, Ninov drew his colleagues this diagram. Picture-perfect alpha decay chains that ended in element 106. If this was legit, the team had found not just 118, but 116 and 114 as well. With the IUPAC decision still out on 114, this was 2, potentially 3 new elements that belonged to Berkeley. Their first in 25 years. Darlene Hoffman was going to get her wish 3 times over. Ninov, in as much disbelief as everyone else, jokingly asked, "Does Robert talk to God?" Now, they didn't immediately announce to the world their finding. They took a few weeks and ran another experiment, and 1 more alpha decay chain was found. Of the 4 they had now, the team reasoned that 1 may be a fluke, but that the other 3 were legit. Not only that, they sent the results to GSI. They also gave the green light. In June 1999, Hoffman and Ghiorso, 2 titans of the element hunt, held a press conference and announced their 2 new elements. The eventual paper was submitted to physical review letters on May 25, 1999. Everyone from the semi-retired Ghiorso to the fresh-faced grad students got to be on it. Viktor Ninov was first author. Given how successful Robert's recipe had been, Ken Gregorich thought that the next logical step was to simply swap out the lead target for bismuth. With that extra proton, maybe they could find element 119. Now make no mistake, if an element was going to be named after someone in the group, it wasn't going to be Ninov. The obvious choice, the one already being thrown around, was Ghiorsium. Al was the current world record holder and the only person who had a legacy comparable to his late friend Seaborg. But Ninov clearly had a bright future ahead of him. With potentially 5 elements under his belt, he was clearly ready to carry the torch. He didn't get to carry it for long. GSI, missing their star researcher but still on top of their game, were eager to get caught up with Berkeley. However, when they took a crack at repeating Robert's magical recipe, they didn't see the alpha decay chain that Ninov had recorded. Similarly, before the end of 1999, teams in France and Japan also came up blank. This was very odd, as all those labs had tried their best to replicate the Berkeley conditions as closely as possible. Robert's recipe was thought to be a long shot, yes, but the benefit of it was low risk with a potentially high reward, as the two recipe ingredients were comparatively easy to acquire and set up. Something was off. Ninov was doing the conference circuit at this time and, again, was bizarrely reluctant to talk about his breakthrough. He continually deflected questions about his potentially career-defining discovery. The Berkeley team is perplexed at this point. They rerun their own experiment in spring of 2000. They can't reproduce the event either. This is a problem now. Assuming the same conditions, the second run in 2000 should have produced around 3 more atoms of 118. By summer 2000, Berkeley established an independent team to rerun the same experiment under the supervision of Yang Li. Completely different team of people, but the same lab and conditions. His studies wrap up by fall 2000. They too saw no evidence of the 118 decay chain. Following this, Berkeley overhauls their detector system and clamps down on their operation procedures. We're talking checking the purity of the helium gas, the resistance of the coils, everything you can think of. They even considered whether their beam was actually made of krypton and not contaminated by some other element. It was in fact entirely krypton, but by this point you couldn't take anything for granted. The year 2000 came and went with not a single hint of 118. By April 2001, they're ready to begin testing their new setup. By May, finally, they got what they were hoping for: another detection of 118. There was only one single alpha decay chain detected, and the reporter, once again, was Viktor Ninov. Now in 1999, Ninov had been the only person to analyze the data, as he was the only one familiar with the GUSI analysis program he had brought over from Germany. But since then, it had been over 2 years, and several people had taught themselves GUSI as well. A postdoc named Don Peterson was among them. He and Ninov would run the program on the exact same data, and yet come up with completely different results. Don's results said 118 wasn't there. The dread had set in. Berkeley by this point knows it's in hot water and meticulously documents every single step from here on out, with multiple rounds of bureaucracy, which I have to imagine is for legal reasons as much as it is for technical reasons. In June 2001, Darlene Hoffman assembles a working group to comb through every bit of data relating to the detection of 118. They are going to sift through every raw data file as far back as 1999. This working group, based on their findings, leads to a new independent review committee, which then leads to a third committee and then a fourth, the last of which has the official name, the Committee for the Formal Investigation of Alleged Scientific Misconduct. Over the course of 3 committees, the investigation had gone from, why aren't we able to repeat the experiment, to, okay, someone is getting fired. A big thank you to Kit Chapman for providing me with nearly 200 pages from Berkeley's internal investigation, which he obtained thanks to California's Public Records Act. As you can imagine, the 3 committees cover a lot of the same ground, so I'll be summarizing their main arguments into 3 categories. 1. Statistical. What is the likelihood that these measurements were genuine? 2. Technical. Is there evidence that the raw data was tampered with, either intentionally or by accident? 3. Identity. If anyone, who is to blame? We'll start with statistics. When the other labs attempted to verify the Berkeley results, they found nothing. This was odd because those labs actually had better beam setups. They had a higher chance at producing 118 than Berkeley. Berkeley was capped at 1.6 times 10 to the 18 krypton ions. GSI and Riken had a combined total of 4.9 times 10 to the 18, which is nearly 3 times as many. If you interpret that statistic in the most generous way possible, that's like being able to spin the roulette wheel 3 times as much. Together, they should have seen around 3 times as many atoms of 118. Again, just like a roulette wheel, this doesn't mean it can't happen, just that it's statistically unlikely. Another physicist, H.K. Schmidt, ran an analysis on the decay chains from an earlier study of element 110, and then compared that to the data from 118. It's important to remember that an element's half-life is a statistical quantity. If you measure just a single atom of a radioactive sample, it will decay after a completely random amount of time. It could be a microsecond, it could be minutes. You need to analyze many atoms and then plot those decay times on a probability distribution. An ideal distribution would see many very short decays and fewer long decays. Data for element 110 agrees with this behavior. When the same test is applied to the 3 atoms shown in the element 118 paper, they rise up sharply, with most decays clumping in the middle of the graph. This data isn't physical. This is goofy. 3 more Berkeley team members privately performed statistical analyses of their own, and out of 1 million random trials, only 0.82% of them gave decay distributions that matched the 118 data. There was almost no chance this data was real. Next, the technical argument. The program used to detect the decay events was called Goosey. Goosey was known to be unreliable at times. It would occasionally glitch, and data could be corrupted in the shared memory database. This corruption could manifest as incorrect histograms, misaligned array indices, or truncated arrays. The problems were frequent enough that an aura of superstition had arisen around Goosey. It took someone experienced with the program to even realize that Goosey had glitched in the first place, much less decipher what it had really measured. But what they were seeing in the data was too perfect to be a glitch. To quote the New York Times, it was as though Microsoft Word had crashed, and like the proverbial monkeys banging away on typewriters, tossed off sentences from Shakespeare. The idea that Goosey had crashed and dozens of lines of measurements had perfectly corrupted to give 5 pristine alpha decay chains was absurd. We're talking time measurements, energy measurements, location measurements, all syncing up to give not just 1 rogue decay chain, but 5. With file corruption ruled out, the only remaining explanation was that the raw data files were manipulated in some way. Whether intentional or accidental, something had happened to the data files that wasn't random. The investigation became hyper-focused on the events that originally showed 118. In 1999, there were 2 runs of interest. Run 13, which was from April 8th to the 12th, detected 3 alpha decay chains. 2 of those made it into the published paper. A couple weeks later, Run 15, from April 30th to May 5th, also detected an alpha decay chain, which also made it into the paper. And finally, in 2001, there was Run 45 from April to May 2001, which showed just a single 2 hand-drawn pieces of paper from Ninov. And yet no one had double-checked where any of these numbers came from. Later, when one of the committees asked Ninov to reproduce figure 2 in the paper, Ninov was able to produce approximate versions of A, B, and C, but he was unable to reproduce figure D using any analysis program, instead saying that he had originally made it by hand. Interesting that of these 4 graphs, only one of these would be easy to generate by hand. Ninov maintained his innocence throughout the entire investigation. Ninov was specifically asked by the committee whether he thought Goosey could have corrupted the data. His answer was no. Instead, he offered multiple versions of a bizarre conspiracy. At first, Ninov argued that someone else at the Berkeley lab must be jealous that the element hunting team was getting so much time with the beam and thus resorted to sabotage. Later, Ninov changed his story and argued that after the initial reports of other labs failing to reproduce the results, someone on the team must have gotten cold feet and retroactively removed the decay chain from the original data. Finally, putting aside sabotage and putting aside someone getting cold feet, Viktor Ninov argued that everyone in the lab technically had access to the account via Ninov. His account password was apparently an open secret. Someone else could have easily used his account, and any blame would fall on him. The committee found that yes, this was possible. Other members of the lab did have access to his files. The problem with this argument then is how did a Goosey expert like Ninov not notice any alterations when they eventually reviewed the data? Similarly, in October 2001, Berkeley submitted a retraction of their paper to Physical Review Letters. PRL declines to retract the paper. Their cited reason is that Viktor Ninov refused to sign off on the retraction. So again, if he believes he's been duped or framed, why would he refuse to sign off on a retraction? Ninov only attended one face-to-face interview on December 14th of 2001 and declined 2 later invitations. His later statements were written answers to provided questions, presumably after he consulted with his legal team. Despite this, some of Ninov's responses verge on outright petty. He claims that several figures in the report by Yang Li are off by orders of magnitude, as a way to discredit them. There's nothing wrong with these figures, they just happen to be based off of Robert's magic recipe, which was well known to disagree with most of the existing scientific literature. And he spends a whole paragraph saying that the committee's focus on the failings of Goosey is comparable to, and I quote here, debates about the superiority of Windows versus Unix, or Word versus WordPerfect. Sure, man. With his back against the wall, Ninov turned on his friends. Whatever friendships they had with Ninov beforehand were destroyed. They wanted nothing to do with him now. The hammer came down quick. Ninov was placed on administrative leave on November 21, 2001, a week before the misconduct investigation began. He was officially fired in May of 2002. After being fired, he filed a grievance with the University of California, Berkeley, but nothing ever came of this. The paper was finally retracted after nearly an entire year. None of his co-authors were implicated in the fraud, although that didn't stop the committee from having a few harsh words for them. They homed in on what they saw as a shocking weak link in the scientific review process, relying on only a single person, Ninov, for the analysis that underpinned the entire claim of element 118. Yes, Ninov was the sole expert at GUSI, but that still didn't prevent anyone from looking at the raw data files. Part of the issue here may stem from the management hierarchy. The experiment was essentially co-led, with Ken Gregorich leading the machining side and Ninov leading the analysis side. As such, he was able to avoid scrutiny. And finally, the lab as a whole was criticized for a stunning lack of documentation, especially for the breakthroughs in 1999, which as we know now, were recorded entirely on just 2 pieces of paper. Heinz Gagler was a friend of Ninov's when they both worked at GSI. Ninov would often crash at his house when they went on hiking trips. Victor was so well received when he came to Berkeley. He had full support, and because of that, one didn't look too carefully into the analysis he was doing. It was a total disaster. Did it destroy Berkeley? Of course it did. Berkeley was Berkeley. The outside world doesn't want fake news. The show was over. Ken Gregorich prefers not to talk about the scandal at all. It was a dark period, and it's gone, and I'd rather leave it at that. It's a similar case for Darlene Hoffman. She never got her element. For those at the top, it's mortifying to have such a blatant case of fraud occur under your watch. And on the other hand, you have a handful of 20-something grad students whose names made it onto that paper. Even if you had just a single shift running the cyclotron during the experiments, your name got on the paper. You had nowhere near enough knowledge or responsibility to even consider fraud as a possibility. And now at the very start of your professional career, your name will permanently be part of a retracted paper. Suddenly, your resume goes from being a golden ticket into any lab you want to a radioactive warning sign. To some, it would be better to just erase 2 years from your career history. And the damage wasn't entirely contained to Berkeley. Sigurd Hoffman had been Ninov's boss at GSI. Elements 110 to 112 had been verified by other labs at this point. The data used in GSI's initial publication